y desde el 2005 es jefe o director del Grupo de Educación y Extensión del CERN. Bueno, forma parte de diferentes comités académicos y demás que lleva una alta dedicación en su trabajo. Así que agradecemos a Rolf por estar aquí, agradecemos a Red UDI en particular por dar soporte técnico a toda esta actividad y a todo lo que ha sido el desarrollo, y en especial agradecimiento al profesor Federico Brum de la Facultad de Derecho de la Universidad de la República Montevideo, porque él coordinó a una serie de intérpretes que ustedes van a estar escuchando aquí, que van a hacer la interpretación simultánea. Ellos son Trenky Eises, Mariana Licio, María Emilia Miller, Eugenia Escanellas, Ana Clara Alonso, Paola Capoto, Ricardo Menéndez y Belén Pancera. Nuestro agradecimiento para ellos. Le damos pie entonces a Rolf para que pueda.
Rolf, whenever you want, you're ready for your presentation. Yes, whenever you want. Yes. Bienvenidos a CERN desde Ginebra. Quiero darles una pequeña introducción a lo que es el CERN y la ciencia que hacemos aquí, las actividades que desarrollamos para el público en general. Llamé esta presentación un vistazo al universo primitivo porque tenemos el mayor colisionador de hadrones, que es el instrumento más grande para la ciencia en el mundo, ¿no? Sorry, Rolf, I lost you. No lo quiero. No, yes. Vamos a hablar de la ciencia de CERN. Y lo que voy a hacer luego, voy a hablar de la organización de CERN y los diferentes impactos que tenemos para la sociedad y el aspecto educativo de las exhibiciones y el resto de las posibilidades que tienen para ver lo que hacemos nosotros. Bueno, lo primero, nosotros empezamos con preguntas muy antiguas que los humanos se han preguntado desde su existencia. ¿Desde dónde venimos? ¿Qué somos? ¿Hacia dónde vamos? Y como ustedes saben, los físicos han intentado durante muchos años responder estas preguntas, pero no siempre se han podido explicar las cosas que podemos observar en el universo. Y entonces, los físicos han intentado responder todas estas preguntas de acuerdo con lo que observan y explicar lo que ven en la naturaleza. Hoy pensamos
our universe comes from the Big Bang. The Big Bang is a unique event in our universe. It created all space and time, and we know rather precisely today that this happened about 13.8 billion years ago. At that time, all the particles in the universe were created, actually in less than a millionth of a second. And you, me, and everything you can see and touch is made out of these particles. So in some sense, in the material sense, we are all 13.8 billion years old, as old as the universe. The event which happened then was characterized by one very interesting phenomenon, namely that energy in form of some kind of vacuum energy, about which I'll talk in a minute, transformed into particles. And to make a long story short, what we are doing at CERN is to simulate that process. We are not simulating it on the scale of the creation of the universe, but on a very, very tiny scale. And it's the tiny scale of the collision of two protons two small particles which are in the core of every hydrogen atom. This is a proton. I animated. We know today it's made out of 3 smaller particles, which we call quarks. These quarks are bound together by exchange of other particles, which we call gluons. And that makes a proton. And you, me, and everything you see is made out of something like 10 to the 29 of those particles. Now, this is in a nutshell the main stages of the evolution of the universe. And as I said, the Big Bang is at the beginning of everything, is about 13.8 billion years ago. And we can say today with rather big confidence that we understand the main parts of the evolution of the universe, starting from the Big Bang itself to the formation of atoms, the first atoms in the universe, which was about 380,000 years after the Big Bang, the formation of the first stars, which was about 200 million years after the Big Bang, and the formation of our solar system, which was about 9.2 billion years after the Big Bang. Our star is a third generation of stars, so we could call it the grandchild of the very first stars in the universe. But what interests us in particular is what happened in this first microsecond after the Big Bang. Because as we know today, all laws of nature came into existence in this very, very short time span. And what happened afterwards was that the universe basically assembled like a big Lego puzzle, but it's self-assembled according to the laws of nature. That means the universe in the end had no other choice than to evolve into what we see today because of the laws of nature which were formed in this first second. And the question is, was that a necessity, and what are these laws of nature which formed them? So that is our goal. Now, in a minute, I will tell you that we have understood a lot about that. But at the same time, there are other things which we know exist and which we cannot explain yet. And I will say that immediately now. We know that 95% of the energy of the universe is made of stuff we do not understand yet. Part of it is called dark matter. Dark matter is something which attracts gravitationally, but does not emit any light, nor does it interact with light. So we can't see it, and that's why it's called dark matter. But we know about its existence because we know that, for example, galaxies rotate much faster than they were allowed to do by Newton mechanics, because we can measure their rotation speed, we can measure how much mass is in a galaxy, and we can see that this mass, which we can observe by light, is by far not enough to explain this fast movement. So there must be more, and we know it's about 5 times more dark matter than there's matter actually in this galaxy. So that is something which we are very much interested in to find out what it is. And in addition, there is something which is called dark energy, something completely different actually. It's some energy which sits in empty space, but on a cosmological level, it makes that the universe expands in an accelerated way. And this accelerated expansion is due to an effect which we attribute to dark energy. And we are very much at the beginning of an understanding of this dark energy. So another very important topic. So what I want to tell you is, in essence, that we know only about 5% of the mass energy content of the universe, but these 5% at least we have understood very well, because there have been 60 years of experiments at accelerators, and these help us to understand what our material world here on Earth is made of. Now, of course, you ask yourself the question, how can we find out with an accelerator what everything is made of? That's a very good question, and I will answer it now. Well, an accelerator has two main purposes. First purpose, the accelerator is like a giant microscope. So we can use little projectiles and send them onto an object like, for example, a proton. And then we can study how these projectiles are scattered when it hits a proton. And this happens, for example, in experiments at CERN. And we could deduce from these experiments that a proton is made out of these three quarks. And these experiments have been made already about 50 years ago, so that is nothing really new. But now it has a second purpose, and that is maybe for us the most important one. By concentrating a lot of energy in a tiny space, which happens when two particles collide at very, very, very high speed or very high energy. If we concentrate a lot of energy in a tiny space, then nature transforms this energy into new particles. New particles which have a mass. It's called, the mass is, in this formula, is m, and the formula E equals mc squared, you probably have heard about it, says that you can transform energy into mass. And that's exactly what happens at our accelerators. And this little animation shows how you create this big energy density, and out comes lots of new particles. And some of these particles, they give you information about actually what happened in the very, very first moments of the universe. I show you now an animation which shows you how when you zoom into a human hair, where are the atoms? You may ask yourself, how small are atoms? Well, they're actually very, very small. So this is a human hair. It's about 100 micrometers in diameter, or 1/10 of a millimeter. And now we see the different parts which are inside the hair. This is a cortical cell. This is a so-called macrofibril, which is made out of tiny so-called microfibrils. And when you look inside of them, there are so-called protofibrils, but these are then made out of a molecule. Now we are at the level of about 1/1000th of a meter. In there, you can see already the molecule. This is keratin, famous when you use shampoo. And there inside, you find the atoms of which we are all made of: carbon, nitrogen, oxygen, and so on. And now we see a little carbon molecule. It contains 6 electrons, 4 of which you can see here in the outer shell. And then you zoom another 100,000 times. So it's a very tiny nucleus inside this atom. And there's the nucleus coming along. It is made out of protons and neutrons. And protons and neutrons are both made of smaller particles, which are called quarks. And they are the red type and the blue type of quark. The red type of quark is called up, and the blue type is called down. And that's basically it, you know. I mean, if you know that there are electrons and 2 types of quarks, you can do whatever you like. You can build all the matter in the universe as we see it. You can build atoms, molecules, cells, humans, rocks, plants, whatever. Yeah? So that's what everything is made of. Now I show you a kind of a periodic system of elementary particles. And I made a blue circle or blue rectangle around the particles which we are made of. These are, as I said, the up quark, the down quark on the left, and the electron. This is you and me and everything. Now our electron has a little cousin, which are the charge, and that cousin is called the neutrino. Okay, so that's the family on the left-hand side. And then we have particles which act like a glue. I talked already about the gluon. This is this three-colored particle on the right-hand side. And then we have another particle called the photon. This is this gamma, which is next to it. And then we have another particles which are called W's and Z's, which are for the weak interaction. But that doesn't really matter. What I want to tell you is that we understand the system of particles and how they are glued together perfectly well today. But there are mysteries. For example, first mystery is, why is this family of particles on the left-hand side is repeated twice for particles with a higher mass, but otherwise identical properties? Okay, so the electron, for example, this blue electron here has a heavier brother, if you want, which is called a muon, which is a Greek sign mu, and an even heavier brother, which is called the tau. We don't know really why that is the case, and so we just put the fact that we know these particles exist, we put in our model, and we can describe it very well. But there's still a mystery about the fact that there are these three families. Now, in the middle of my graph here, you see a thing, a kind of a snowball, which we call the Higgs boson. Now, you may have heard about the Higgs boson. The Higgs boson is the excitation of a field, which, no surprise, we call the Higgs field. And that field actually fills our entire universe. And the particles, by interacting with this Higgs field, obtain their mass. Well, that was a theory until about 4 years ago, because nobody actually knew if this theory was correct. But 3 years ago, or 4 years ago, we could prove that this Higgs boson, which is an excitation of the Higgs field, actually exists. And the proof, or the fact that we could find that particle, was a proof that the Higgs field exists. And it was a big discovery, and it basically completed our understanding, as far as we describe it with formulas, of the structure of matter. But as I said, there are still big mysteries. Dark matter, dark energy, and many, many other details, detailed parts of the evolution of the universe, which we do not yet understand. And so that is basically the situation today. So now that was the first part of my talk. And now I want to describe you a little bit about the installations we have at CERN and the organization which runs these installations and provides the infrastructure for 10,000 or more physicists from the entire world working here. What you see here in this beautiful aerial view is this Geneva. You see in the middle, you see the lake. The mountain, the highest mountain behind you is the Mont Blanc. And then you see something which looks like an airport, that is the Geneva airport. And then you see a yellow line which we drew on the surface of that picture. And this yellow line represents the place where the LHC runs, 100 meters underground in a tunnel. And then now when we zoom in, we sort of superimpose the tunnel onto this picture. So now on the left-hand side, you see the LHC, and on the right-hand side, now disappeared, you have seen the area through which it runs. The LHC is a huge accelerator. An accelerator is a relatively simple device in principle. In detail, it's very complex. In principle, it's very simple. You take an electric field in one place. With this electric field, you can accelerate particles when they traverse an electric field. So a positive particle is, for example, attracted to the negative electrode. And in this process, it gains energy. And we do that once. And then we put a lot of magnets which bend the trajectory of the particle And we do that in a way that the particle comes back after a short time. It does one revolution, come back to the place where there is the electric field, then we give it another push. So that was push number 2. So the particle runs around the circle another time, and we give it push number 3. Every time it runs through the electric field, it gets another push and it gains energy. And so we repeat that process in the LHC 11,000 times a second. That means even though the LHC is 27 kilometers in circumference, a particle only needs a very short time, a tenth of a millisecond, to go through it. So we repeat that 11,000 times per second. And every time it goes through, the particle gains energy. Because of relativity, or relativistic effects, the particle does not get faster. It cannot reach the speed of light exactly, but you can go closer and closer and closer. The particle then doesn't get much faster, but it gains energy, which is actually observed as a mass increase. And since this mass increase means we also have to increase the magnetic field in order to bend it on its track, we need a very, very strong magnetic field in order to keep it on track. And that is the purpose of these magnets in the LHC. It took about 10 years to build magnets which could do that. And it is a very big technological feat that this happened. Now, that is our purpose, to provide the infrastructure for the world in order to use accelerators and collider, actually, because there are 2 beams which collide in 4 interaction points. And we provide this installation to countries, first of all to our member state countries, but in principle to all countries in the world. The member state countries are the ones which pay us with a membership fee. And we have right now 22 countries, which you can see here on the slides. They are mainly European countries, but recently there's also Israel and Pakistan who have joined us. There are many countries which are in a waiting loop in order to join us maybe at a later stage, which you can see here: Brazil, Russia, Cyprus, Turkey, Ukraine, and so on. And then there are some observer states which provide special contributions to us. Now, CERN is, as I said, an infrastructure. CERN does not employ many physicists. I'm kind of an exception, actually. But it has 2,300 staff, roughly, of which mostly people are engineers and technicians. And, of course, administration. Then we have about 1,000 people who work on short-term contracts, like fellows and associates. And then we have more than 11,000 scientific visitors. These are the scientists which come from all over the world, including many also from South America. And they do experiments here at CERN. Now, all that costs money. Our yearly budget is roughly 1 billion Swiss francs, which is roughly $1 billion nowadays. So that sounds a lot, but it is actually not so much. It is basically the budget of a medium-sized university that has about the same budget. Big universities have budgets which are up to 5 times higher. Now, this is just an example of the complexity of the instruments which you are building. This is a cut through one of our dipole magnets. I don't want to go into details, but the development of these magnets, which make up basically our accelerator, took us 10 years because it's extremely complicated to build these things. Just to know, it's interesting that, for example, these coils which produce the magnetic field, they have to contain a current which is about 12,000 amperes. Now, such a current can only flow through the coils if these coils do not have any resistance, Ohm's resistance. Because if they had, the current would create so much heat that the coils melt. And we don't want that. So what we are using is a special effect which is called superconductivity, but that only happens when these materials are cooled down to something like almost absolute zero, exactly 2 degrees above absolute zero, and that is, after all, minus 271 degrees. But to do all that and keep it in a stable state and to protect it from the radiation which comes from the outside, it was very complex. Okay, now coming to the next point, what do all these scientific visitors do? Well, they built cameras. These are the cameras which observe the new particles which are produced in the collisions. So imagine there's a collision, there's thousands of new particles produced, and they are running through the detector. Now the detector is, as I said, a huge 3-dimensional camera. And huge means huge. These detectors are the height of a 6-story building. They are 26 meters high, this one here, and 42 meters long. And they are not empty anymore. That was in 2006, that was 10 years ago. They have been filled with 100 million sensors, which fill the entire volume, which you see here still empty. Now, these detectors not only have they to detect particles in huge numbers and to track exactly what is their path and measure the energy and the momentum of each track to a precision of the size of a human hair. No, they also have to do that extremely fast, because we know that the processes we are looking for example, the discovery of the Higgs boson, they only happen in extremely rare cases in these collisions between 2 protons. To give you a number, you have to collide 2 protons 10 billion times in order to have probability that one of these so-called Higgs bosons is produced. So that's extremely rare, but in order to have a chance to see many of these Higgs bosons, we have to produce many billions, even trillions, and maybe you don't even know that word, quadrillions of collisions. A quadrillion is one with 15 zeros, okay? So these cameras basically are able to take snapshots of 1 billion collisions per second. So you can imagine how much data that produces. But we have to be able to digest and sift through these data in order to find these rare events which we are looking for. Now, this worked. It really worked. No, and that was, even for us, a positive surprise. A prediction from Peter Higgs, who proposed the existence of this so-called Higgs boson, has been made in 2012. And it was necessary to go through something like 3 quadrillion events, so that means 3 million billion events, in order to find it. And these scientists from all over the world, they went through these data and they found it. Now you may be wondering, how does it all work together? How do I get a proton into the LHC, and how does it is accelerated and so on? So I will show you now a little animation. I hope you can see it. Okay, now we are starting. We are here at CERN. You have seen the overview. And now we are zooming in to the very first stage of the acceleration. It comes from a hydrogen bottle where we ionize hydrogen atoms and the protons come out, and they're accelerated in a few pre-accelerators, which are called linear accelerator and booster. Now from there, they are injected into our first injector accelerator, which is called the proton synchrotron. So they get a push or many pushes here in order to sort of be able to be injected in the second one, which is called the super proton synchrotron. And from there, it goes now into the Large Hadron Collider, the LHC, where you have two beams counter-rotating, and they collide in these detectors. Voila. And now you see there's 4 different detectors called CMS, ALICE, ATLAS, and LHCb. And there we have an enormous amount of data, which are all sent out. And then from there they are filtered. And we are selecting only 1 out of 1 million data, which are sent to our computer center. In the computer center, they are then copied, because it's very important to copy these data and keep them so that we can analyze them later. And then they are sent out to a huge network of computers which are distributed around the world. Today, this network has more than 500,000 computers. That allows us to reconstruct these information from all these sensors and make sort of sense out of it. And you see here the frequency. This happens, as I said, 1 billion times a second. And this allows us finally to analyze the data, which we then sort of publish. And that was basically, in a nutshell, what we are doing. Now, who are all these physicists, these 12,000 or more scientists which come from the entire world? Well, you can see there are about 8,000 or so, 7,600, which come from Europe. But all the rest comes from other countries. Well, you can see South America is also in there. So we have, for example, 20 scientists from Argentina, 3 from Bolivia, and 23 from Chile, 40 from Colombia, and so on and so forth. In Uruguay, we have 1. So still room for improvement here. Okay, now you ask yourself, okay, does this have any practical applications? You know, it's very nice to be curious and so on, but can we use that technology for something? Well, the answer is yes. Already in the 70s, CERN research has contributed a lot to, for example, building one of the first PET scanners, a positron emission tomograph. And that is something, a device which stands now in 10,000s of different hospitals. And it allows you to look into the brain, for example, but it also allows you to find tumors, which are somewhere in your body. And that is an application which really saves lives. We also use accelerators and proton beams in order to treat cancers. You know, there are several, sort of right now, something like 50 therapy centers which use accelerators like we have here, and they are used in order to send proton beams onto, for example, brain tumors, and then they can destroy these brain tumors without surgery, you know, and that is a very important thing. But of course, the application which probably all of you know, and which comes from CERN, is the so-called World Wide Web. It was developed here at CERN in 1989, and then given into the public domain in 1993. And that is an application which sort of now is used worldwide. Of course, you're using it too. We are using it today. And this really made a huge contribution to the world economy. There was an estimate by McKinsey in 2012 that just the grid alone contributed to something like almost 2% of the world GDP, which is a huge number. It's like $1.6 trillion per year. So that's our contribution to the world economy. Now, we hope that the grid technologies, which we have pioneered as well, they will also have an application which everybody can profit from. It's a little bit the pre-stage of cloud computing, which now has more and more meaning for everybody of us. Okay, now I'm coming to the third part of my talk, which is about education and outreach, something which is close to my heart nowadays. In last year, we had 107,000 visitors which came to CERN and could go on a guided tour. That's a lot. We make a huge effort in order to accommodate everybody, but that's not possible. We get about 300,000 demands. So we are doing our best, but there's still room for improvement. Usually our guides, we have about 200 guides, they're all volunteers. They are scientists which take some time in order to guide visitors, because we know all the general public funds us by their taxes. And so we think it's very important to give something back to them. Now, many of these visitors are school classes, and most of them come from far away. And so we are also trying to use our science and our enthusiasm and our curiosity about the universe in order to inspire young people to become interested in science. So we have built exhibitions in many different places, and these exhibitions not only show nice animations, but they contain also some interesting effects, so you can see the authentic places. Here, for example, the computing center, which is hidden behind this intelligent glass. A similar thing we have in different other places, but then we have also permanent exhibitions. For example, this one is a permanent exhibition in the globe, which we call Universe of Particles. And it's basically showing the mysteries and the curiosity which humans have in order to understand their origins. And then we have another exhibition which shows the nuts and bolts of our research. So we have a model of the LHC, and we have big screens integrated into the authentic pictures. On these screens, you see real people talking about their own lives here at CERN and what they are doing. Now, not everybody can come to CERN, so we come to them. So we have traveling exhibitions. We have one which is called Accelerating Science. And this exhibition is pretty big, 450 square meters, and it travels around mainly in Europe and goes to 2 to 3 countries per year. Now, this is a little map of Europe showing where we have been. So we have been from the furthest west, which is Galway and Portugal, to the furthest east, which is actually beyond Europe. We have been up to the state in the Caucasus, which is, for example, Azerbaijan and Georgia. Okay, now, particularly teachers are very close to our heart, because we know that students coming to us, we can maybe interest them, we can inspire them, but, well, they will see that as a kind of entertainment, and they look at us for a moment, they see some enthusiastic scientists, but when they go away, they forget pretty quickly about us, so we know that. On the other hand, teachers are standing in front of their classes for 2 to 3 hours every week for 2 to 3 years. And so if we manage to get the teachers on board, and we make teachers into enthusiastic teachers and ambassadors for CERN, then we reach the students, the school students, much more and much more efficiently. And so we have now, since 2006, we have arranged courses for more than 10,000 teachers from all over the world, which have followed our courses. And from evidence, anecdotal evidence, and from the feedback we get, we know that this really helps to transmit our enthusiasm through the teachers into the classroom. So that's one thing which we devote a lot of time to, and we have a lot of teachers coming from all over the place here to CERN. They follow usually 1 week programs. And then in addition, we offer to the students which come here, to some of them at least, we offer the possibility to do experiments on modern physics, here at our so-called school lab. And in this, we can sort of accommodate something like 4,000 students per year. And then, of course, we also have programs for university students, but they are more already advanced. They are sort of in the second or third or fourth years of their study on high energy physics, computing, and accelerator technology. Now let me go just explain a little bit more about our teacher programs. I mean, the first thing which we do during this week is to give them an update on their knowledge. As you may know, teachers learn a lot about classical physics at university because that is the main curriculum which is taught at schools. We do not think that is the best way to do it, but that's how it is in practically all countries in the world. What we are trying to do is to show the teachers what happened in the last 100 years of physics, because nowadays we know so much more about the matter and the universe than 100 years ago that we think it's a pity that this knowledge is not transmitted to the general public, to everybody. So we give them lectures on CERN, particle physics, cosmology, antimatter, and everything that has to do with the CERN's research here. We bring them to the different places where we do the research, so they see the installations in their real size. And then, of course, we do activities with them. We build a cloud chamber, and we do lots of question and answer sessions so that they can ask us and we reply them in their own language. And we mean it. We have most of these courses in the national languages of the teacher. Here you see the evolution of our program. So our education group was founded in 2005. And since then, we have ramped up the number of teachers to something like 1,000 to 1,200 per year in something like 36 or more programs. So this is a major activity of our group. And here you see that, again, teachers in our programs come from the entire world, you know, again, from all over the place and including South America. You know, we had teachers from there as well, you know, and 4 from Costa Rica, a lot from the Dominican Republic, which we have a special program for, and many other places. Now coming towards the end of my talk, I want to point out a few things which may be of interest to everybody of you. I mean, we have, for example, a worldwide competition, which we call Beamline for Schools, which usually starts around now and runs until March next year. And we ask teams from schools to make proposals what they would do with a beam of particles at relatively low energy, of course, which consists out of matter particles, antimatter particles, pions, kaons, antiprotons, and so on and so forth. So they have full freedom to come up with an experiment with particles on particle physics, and we provide them with the detectors and the software and the control systems that are needed to do that experiment. So it's great fun for them, but of course only one can win, or 2 actually. And so we get usually something like 200 to 300 applications, many good ones, and then we sort of select one out of these, or 2 actually in this case, and then we invite these 2 teams to come here to CERN and do actually this experiment. And that was very successful in the past, and we repeat it again and again every year. Here, just to show you, that is our so-called school lab, and these are the experiments that you can do. I don't want to go through every single one, but it has really to do with fundamental classical experiments, which were at the foundation of quantum physics, and then you learn about detectors and other technologies which are relevant to this field of science. One thing not to forget, I mean, in order to reach a public which may not initially be maybe interested in physics, but is maybe interested in arts, we have an Arts at CERN program here, which consists of different branches, but it has in common that we offer residency programs for scientists for 3 months, for 1 month, or just for 1 to 2 days for a visit. And these residency programs, they are funded by our sponsors. And this funding is competitive. That means the artists have to apply, and then a cultural board selects the best applications, and then these artists can come to CERN for 1 to 3 months, and they have find an inspiration partner here, another physicist, and they can then find out what we are doing. We call it creative collisions, you know, and then we hope, or we see evidence that these artists produce works of art which are inspired by the science of CERN. And that program is really working very well. We have many applications. Sometimes we have something like 900 artists applying for one residency. You know, so it's a really very popular program. And it allows us to reach a public which may be not initially interested in science, but through the arts we can draw them in to become more interested in the questions we're trying to explore. And last but not least, we offer remote visits. That's exactly what I'm doing right now. You know, I connect with you through the internet, and you have the possibility to see me, to answer questions. I can answer your questions, and we do that a lot, also with school classes, with Google Hangouts, and so on. And it's a very cost-effective and also inspiring way to connect with people which are very far away. Okay, so this is my last slide. I'm just summarizing that we are making a large effort to communicate to our stakeholders, in particular the general public, that education and outreach programs are very important to us, that the CERN Visit and Exhibition program is a very large one. And well, we are really trying to bring modern physics into school. So now, basically, we are looking forward. In 2016, we have been running very successfully at higher energy and higher intensity, and we hope that we can say something about new discoveries in the near future or the medium-term future. But as you know, nature is sometimes very secretive, and we cannot really tell you if or if not we will find something new in the next few years. But we, of course, hope very much that we do. So thank you very much for your attention, and I hope that the transmission was successful. Thank you.
Asking you some questions, if you're okay with it.
Vamos a pasar a las preguntas. Habilitamos las salas con micrófono, o si no, aquellas que nos quieran mandar por el correo electrónico, las compilamos, las leemos y Rolf las podría contestar. Así que no sé si de pronto podemos habilitar el micrófono de la sala de Facultad de Ciencias, que estaba ahí. O el Centro Regional de Rivera, que estaban conectados.
Hola, Delma.
¿Sí?
Hay varias preguntitas, pero de entre ellas, ¿qué nuevos desarrollos tecnológicos podemos esperar en función del avance de las investigaciones del CERN a corto plazo?
¿Podrías repetir, por favor, qué nuevas?
Esperar en función del avance en las investigaciones que se desarrollan en el CERN a corto plazo.
Perfecto, desde el Centro Regional de Rivera, en Uruguay.
new technological advances can we expect from CERN in the near future?
Yes, which new technological advances can we expect from CERN in the near future? Estamos trabajando en nuevos tipos de detectores que nos permitan grabar datos más rápidamente y también para operar en ambientes más difíciles, con radiación. Si vamos a energías más altas, a intensidad más alta, más radiación. Entonces, y también otros segmentos de mejora en los sistemas de control, electrónica, datos, adquisición de información y tecnología. Todo suena muy especializado, pero toda esa tecnología encuentra aplicaciones dentro de la sociedad. Así que estamos trabajando juntos, por ejemplo, en el área de computación. Tenemos algunos proyectos que están sobre la nube. La nube de la computadora es algo que no solo es útil para científicos, sino que cubre todas las áreas médicas, prevención del cáncer, prevención de tumores, proteínas, protones, muchísimas cosas que podría nombrarles 30 o 40, que afectarían nuestra vida diaria. La tecnología superconductora, tal vez un día, la podemos usar para transportar energía de A a B. Y por supuesto que también está todo el campo de aplicaciones médicas. Por ejemplo, estamos intentando construir un acelerador que pueda acelerar partículas en menos distancia, más compacto, y se puede usar para tratar tumores. Tratar los tumores con esas partículas es mucho más sano que usar, por ejemplo, radiación que se usa ahora. Porque los haces de partículas pueden enfocarse en un lugar sin destruir todos los tejidos que hay alrededor. Entonces, diría que hay muchísimos desarrollos tecnológicos y aplicaciones que van a salir desde el CERN. Pero los que son más importantes no los conocemos todavía, porque eso se va dando. Cuando se inventó el Internet, que estaba acá por 5 años, hasta que realmente salió al mundo. Y luego realmente salió al mundo. En los últimos 15 años ha crecido exponencialmente. Y ahora más de la mitad del mundo lo está usando. Así que quién sabe lo que puede resultar de la investigación en los próximos 2 años. Thank you, Rolf.
¿Alguna otra pregunta en la sala? See if there are any other. Sí, adelante.
Delma, mientras llega otra pregunta, ¿podemos hacer otra?
Sí, adelante, Jorge. La sala que está para preguntar, por favor, prepare la pregunta y el equipo.
No,
Adelante,
sí,
Jorge.
si respecto a esos desarrollos que mencionó, ¿alguno de ellos está vinculado a la computación cuántica?
And are some of the developments related to quantum computing? Yeah, let me check. He said, quantum computing?
Si podés ampliar un poquito más lo de computación cuántica.
Bien.
A ver si afinás un poquito.
Sí. Bien. Hace un tiempo yo hice una pasantía en computación cuántica y que estaba directamente relacionado con la biología. Y dado que desde el CERN están desarrollando aplicaciones médicas, quizá un punto de contacto entre el desarrollo en cuanto al tratamiento, almacenamiento y procesamiento de la información a través de las computadoras y esta otra línea de investigación que vincula el desarrollo de computadoras cuánticas biológicas, quizá si había algún nexo entre lo que ellos hacen o no, directamente.
Okay, the question was related to biology. If regarding the developments of treatments and filing of data, if there are any new developments related to that. Lo que hacemos es usar computadoras masivas. Estamos teniendo un problema que aparecen muchísimas copias y tenemos que reconstruir la información. Así que de cierto modo estamos analizando 500.000 eventos de colisiones en diferentes computadoras. Así que la computación es algo paralelo en lo que hacemos. Tenemos un problema muy complejo. Tenés una computadora cuántica que busca millones de cosas. Así que son lados del espectro completamente separados. O ves al lado de nuestro problema, o sea, muchos datos para almacenar, o deseas que algún día una computadora cuántica, que es muy práctica, exista. Pero lo que ofrecemos ahora es básicamente una gran cantidad de computadoras que pueden masivamente resolver problemas. Es una posibilidad, pero en el CERN no es muy útil en este momento. A realizar un análisis estadístico de cierta distribución de incidentes. Y eso podría realizarse en un sistema de computadoras. Thank you, Ross.
Que esperen. ¿Alguna otra sala que quiera consultar, hacer alguna pregunta a Rolf, tanto específica sobre temas de física como sobre lo que nos explicaba de los diferentes programas educativos de extensión? ¿Alguna otra sala? A mí me gustaría preguntarle a Rolf por el programa educativo que tienen en República Dominicana, que dijo que era un programa especial o específico, si puede ampliar. Porque ahí tenemos varios contactos que participan activamente en nuestras actividades.
To know more about the education program in Dominican Republic. Bueno, empezó por el vicepresidente de República Dominicana, que se contactó con el CERN y estaba muy interesado en nuestra oferta para capacitar docentes, porque aquí en República Dominicana hay una gran necesidad de capacitar docentes y ayudarlos a hacer cosas científicas y de física en las escuelas. Entonces hicimos un acuerdo bilateral entre el CERN y República Dominicana y les dijimos que nosotros vamos a aceptar a capacitar a aproximadamente 30 docentes por año de República Dominicana, y el presidente o el Ministerio de Educación paga los viajes, el alojamiento y otros gastos. Entonces este fue el acuerdo. Esto es lo que hemos hecho en los últimos 3 años. Entonces tenemos clases para estos docentes y lo hacemos efectivamente por 5 días, empieza un lunes hasta el viernes. Ellos generalmente vienen el fin de semana y se van el siguiente fin de semana. Entonces, yo creo que esto ha sido un programa bastante exitoso. Thank you, Rolf.
¿Alguna otra sala que quiera hacer alguna consulta, alguna pregunta? Mientras preparan sus consultas, les comentamos que hemos hecho una serie de propuestas a Rolf para trabajar a través de la red, así que la próxima instancia va a ser entre nosotros, entre los que estén interesados en la red, de participar para generar propuestas y acciones conjuntas. ¿Alguna otra sala? ¿Alguien que quiera decir o saber alguna otra cosa?
Hola, ¿me escuchan?
Sí, te escuchamos. Adelante. Sí, puedes presentarte.
¿Me escuchás de Uruguay, Durazno? ¿Me escuchas bien?
Sí, muy bien. Adelante. Adelante con la pregunta.
Bueno, muy interesante todo lo que los jóvenes están presentando. Presencié todo lo que ustedes dijeron. Soy directora de la Escuela 32 de Durazno, con chicos de 4º año, pero ya se fueron 4 años de escuela, estuvieron muy interesados, así que felicitaciones a todo el equipo, y bueno, mañana estaremos tratando de aterrizarlo, de bajarlo al programa escolar. Un abrazo y felicitaciones nuevamente, gracias.
¿Alguna otra sala? Muchas gracias, maestra. Seguimos en contacto, activando y apoyando todo lo que ustedes puedan realizar ahí, así que tenemos sus datos y vamos a seguir en actividad. Gracias, maestra.
Buenísimo. Disculpa que no pude escuchar la devolución porque no tenemos fibra óptica todavía en la escuela, simplemente tenemos el módem privado. Bueno, pero la verdad que los felicitamos. Gracias a ustedes por la innovación. Cariño.
Gracias. ¿Alguna otra sala? ¿Alguna otra sala que quiera participar o que quiera preguntar? ¿México?
Delma,
Hola.
Perdón,
hay más de México, sí.
Sí, adelante.
La Facultad de Ciencias de Uruguay quiere preguntar ¿cómo puede aplicar un estudiante para las estancias o alguna beca?
Ahí está, qué bueno.
Rolf? So students from the School of Sciences in Uruguay want to know how can they apply to different internships or programs at CERN. Eso depende un poco de distintos factores. En primer lugar, no estamos ofreciendo pasantías o trabajo a estados no miembros, lo que en realidad excluye a muchos países. Eso significa que desde Uruguay sería difícil solicitar, por ejemplo, una pasantía de verano directamente, pero hay excepciones. Por ejemplo, tenemos un pequeño programa que se llama Estudiantes de Verano para Estados No Miembros, que es un programa al que pueden solicitar y es para pasar entre 8 y 30 semanas en CERN para escuchar charlas en la mañana y luego hacen actividades de investigación en la tarde. Pero esto implica que tienen que conseguir financiamiento de su país para ir al CERN. Y bueno, son seleccionados por un comité de selección en su propio país y luego pueden venir al CERN. Pero esto es un proceso muy competitivo. Otra posibilidad es que una universidad que exista en un país que ya tenga investigaciones en CERN, entonces pueden venir en vez de como cliente, se dice cliente de esa universidad a CERN y van a ser bienvenidos, por ejemplo, pueden trabajar aquí, pero en principio van a estar bajo la supervisión de su universidad. Entonces, CERN solamente puede ofrecer un número muy pequeño de pasantías para estudiantes y técnicos e ingenieros de Estados miembros. Entonces, así es como funciona, porque por supuesto que los Estados miembros son los que nos financian, entonces por supuesto que ellos quieren tener más oportunidades en estas posibilidades. Thank you, Rose.
Gracias, Facultad de Ciencias, por la consulta. De paso aclaro que en el 2014 nosotros iniciamos una serie de trámites para que, como justo el del 2014 estaba parado el colisionador, o sea, no se estaban generando, bueno, investigaciones específicas de colisiones, porque bueno, se estaba reconfigurando todo, se abrió mucho más las posibilidades de visitas y ahí fue que nosotros hicimos gestiones para que un grupo de estudiantes y docentes pudiera ir y bueno, realmente fue una pena porque hubo una parte de autoridades que les interesaba y otra que bueno, que no hizo mucho caso a esa posibilidad que abrió el CERN y de hecho el mismo Rolf lo posibilitó y demás, pero me parece que esas cosas son las que hay que trabajar en conjunto y que desde la red poder apoyar no solamente en la difusión, sino también en la necesidad de la formación de físicos y de la formación en cultura científica en ese sentido. De paso, agradezco a Gabriel González Strindberg, que él siempre ha estado en todas las actividades que hemos hecho, y bueno, y cuando se refirió a que es el único científico, evidentemente se estaba refiriendo a él, ¿no? El científico en Uruguay. Así que me parece que esas son las cosas que de pronto la red, en cuanto a conjunto, en cuanto a otro tipo de movilizaciones, podría apoyar o generar o ver vías, ¿no? Ya que algunas puertas están aparentemente cerradas. No sé si alguien más quiere hacer alguna pregunta, tanto por el chat de la interfaz que ustedes tienen ahí o a través de videoconferencia. Si no hay más preguntas, sí, adelante.
Hola, soy Isabel Pedraza de México. Yo soy representante adjunta de la colaboración CMS de la Universidad de Puebla, en México. O sea que tenemos contacto con el CERN, la universidad. Somos miembros de la colaboración CMS. A mí me interesó el programa porque hay, como ustedes mencionaron, hay ciertas zonas, a pesar de que sí podemos enviar estudiantes que ya están en la licenciatura o que ya están en la universidad o de posgrado, hay ciertas áreas que no están eficientemente desarrolladas, como en el área de preparatoria, antes de llegar a la universidad. y que es en donde a mí me interesaría hacer como poder también aportar, ¿no? Tenemos algo que se llama CMS Masterclass en el CMS, por ejemplo, que se pueden desarrollar en diferentes países y es un día concentrado con los chicos para que hagan un poquito de análisis de datos como se hace en el CMS. Entonces, aparte de que estoy interesada en cualquier actividad que salga de esta red, también me gustaría apoyar en lo que se pueda para poder llevar a cabo actividades que puedan mover, pues, que aumente la sinergia de esta red.
A person from that works in the CMS and wants to know more about high school activities and master classes and data analysis. Bien, estas masterclasses esto pertenece a la parte de la extensión del CERN y toma lugar entre febrero y marzo y consiste en un programa en el que se puede obtener datos de uno de los 4 grandes experimentos y es un programa de obtención de datos bastante simple. Además de este ejercicio, previo al ejercicio mismo, presenta una introducción al campo y de lo que se puede aprender del ejercicio también. Hay 45 países distintos que pueden acceder a este programa y no está seguro de que México sea uno de ellos. Cualquier cosa que se le puede escribir a su correo electrónico y dice que se le reenviará ese correo electrónico a la persona coordinadora de esas actividades.
Bien, si no hay más preguntas de las salas, ya no hay más preguntas en el chat, estaríamos cerrando esta actividad. No sé si vuelvo a consultar si hay preguntas por videoconferencia. Si no hay más preguntas. Adelante.
Isabel Pedraza dice que México tiene el programa, pero que ella se refería a otros países.
No more. She would like to know more about other countries apart from Mexico that can access to these kind of programs or outreach activities. Sí, dice que pueden ser 45 países distintos. Estados Unidos, Australia, Japón, por ejemplo, otros países europeos. Hay una gran lista de países. Si quiere, dice que puede enviar un link y pues se puede ver la organización sobre los países que toman parte de este tipo de programa.
Bien, y a su vez, ¿cómo los países se pueden involucrar? Es lo que pregunta Isabel.
She also wants to know how these countries can be involved in these activities.
Por el ministerio, ¿cómo
through the ministers or the ministries, or how? Just send, solo enviar un correo electrónico a él o al coordinador del programa. Y luego van a recibir un mail de ese coordinador. Solo necesitas una computadora, una pantalla y un proyector. Y conexión a internet. Eso es suficiente.
refiriéndose a las visitas virtuales.
Claro, respecto a las visitas virtuales.
Bueno, estamos cerrando entonces por aquí. Rolf, thank you very much. Estamos cerrando. Agradecemos a Red Cudi por todo el apoyo, por todas las pruebas que realizaron, a todas las salas, al profesor Federico Bruno y sus estudiantes, sus intérpretes, que bueno, han hecho un trabajo impresionante. Muchísimas gracias, realmente, muchísimas gracias. Y estaríamos siguiendo próximamente en alguna actividad, muy próximamente, en alguna actividad para un nuevo paso de la red de Amigos del CERN. Así que queda inaugurada formalmente la red y esperamos tener la participación y el interés de muchos de ustedes. Así que la difusión también es importante. Muchas gracias.
Gracias por dejarme hablar aquí y espero que los haya ayudado a poder saber más de lo que es el CERN y espero que alguna vez puedan estar aquí como visitores, como visitantes y que hayan aprendido más sobre la ciencia en general. Gracias.
Gracias, gracias.
Chao.
Ay, gracias. Muchas gracias a las salas. Seguimos en contacto entonces. Les enviaremos próximamente algún resumen de esto y recoger sobre todo las iniciativas y los intereses de ustedes. Muchas gracias.